Hello everyone and welcome to lesson 17 on the Save My STEM Physics channel. This is lesson 4, I believe, of the wave interaction section of the course for AQA level physics. And today's lesson is about optical fibers or fiber optic cables. So optical fibers are cables or fibers which are used to transmit information through the use of electromagnetic waves, which is why it's in the waves section of the course. Um, and the way that they work is they are incredibly thin fibers, which, using total internal reflection, reflect a wave through the fiber, round corners and things like that, so that you can transmit information not just in a straight line, but across the world, right? Um, and so to give like a general image of what a fiber optic cable will look like, you'll have a central fiber, which we call a single mode fiber, basically an incredibly thin fiber. And this is also called the core, so the core is made of a single mode fiber. And then we have an outer section called the cladding. So if I just do this to represent that, you have the two top parts, which are the cladding, and the central bit is the core. And if we go over our fact of total internal reflection, our conditions, we're going to require that the refractive index of the core is greater than the refractive index of the cladding, so that total internal reflection can occur. And what's going to happen is light or any other electromagnetic wave is going to enter our core, and it's going to hit the top, and it's going to reflect off at the same angle, and then it's going to keep doing that at the roughly, well, it will be exactly the same angle. I haven't drawn that perfectly here, but that does the image justice, and that is just a ray which is traveling through the fiber optic cable. So not only is the cladding there so that it will have a refractive index lower than that of the core, so total internal reflection can occur, the cladding stops. Oh, this pen is not. This pen. I've been saying this pen's going to run out for a very long time now, and it still hasn't, but it probably will soon. Uh, Cladding stops contamination or like damaging of the core. So if your finger touches the core, you will leave some grease on the core that will have a different refractive index, and that will change the way that the light reflects or refracts. Um, Same thing would obviously happen on the top of the cladding, but the light wouldn't hit the top of the cladding, so the grease from your finger wouldn't affect it in the same way that it would if you got the grease of your finger onto the core, for example. Um, what else is there that you need to know about the cladding? I guess all you need to know about the function is that the core is where the electromagnetic wave travels, and the cladding is a material of greater, no, sorry, a material of lesser refractive index, such that the electromagnetic waves will totally internally reflect. But there are some issues that come with fiber optic cables, and one of these is signal degradation. So signal degradation is caused by something called absorption. And that's when, as the light hits the boundary, or the boundary between the core and cladding, some of the particles in the cladding absorb some of the wave, decreasing the strength of the wave, right? And if this happens too many times, the pulse will get too weak to be noticed by what is trying to intercept the signal. So we can represent pulses in terms of like the strength of the pulse on a graph like this. So say we just have one pulse, And boom, here's our pulse. We represent this with a rectangle. We have a pulse like this, right? So this is just a graph. Here, there's no pulse. Here, there's the pulse, right? But, so this is the pulse as it enters the cable. But when it's reaching our interceptor or our satellite or whatever, it wouldn't enter a satellite, but you kind of get the gist. It might look something more like this. You'll see that it's in the same place. It's got the same width and everything. It's just smaller. It's got a lower intensity. And this may still be intercepted, but let's say that the wave traveled so far and bounced so much that the pulse only looks like that. That probably wouldn't be intercepted, that wouldn't be noticed. And this is one of the massive issues with fiber optic cables, is how do we sustain this pulse? And the way that we do this is through the use of something called a repeater. What a repeater does is, let's go back to our example here, our first example, where we have the height, that largest pulse, the original pulse, and then it'll end up something like this, the middle one. When it reaches the middle one, we'll use a repeater, and that will log that pulse and give that exact pulse, the middle pulse, just of greater intensity, effectively restoring it to what it was. That's not a very great drawing. That should be identical to that drawing. So what the repeater does, as I was saying, is it logs that pulse uh, and then repeats a pulse of greater intensity, effectively equal to the first pulse that was given to the cable. And that's all the repeater does, and that fixes this issue. But another way that signal degradation happens is through dispersion. And dispersion is a little bit more tricky to deal with because there's two types of dispersion. There's modal dispersion and there's material dispersion. So, modal dispersion is when light enters at different angles, so it takes longer paths. So, for example, this light ray could perfectly exist in a fiber optic cable, but so could this one that just traveled. That's a really wonky line, but imagine that just traveled straight through the middle of the fiber optic cable. That path is going to be shorter than the jagged path that this other ray takes, right? But both the rays are going to travel at the same speed. So the ray that travels at the jagged path is going to take a longer time to reach the final destination. Speed equals distance over time. Distance increases, speed is constant, so time must also increase. So that's modal dispersion. I'm just going to write modal there. Right, and the way that we fix modal dispersion, you might think is counterintuitive, but it actually makes a lot of sense. We make N cladding, so the refractive index of the cladding, as close to the refractive index of the core as possible. So say the refractive index of the core is 1.3, we would say that the refractive index of the cladding is about 1.4 or 1.5 would be optimal. Because what that does is that increases the critical angle, which is something we discussed in the last lesson. That increases the critical angle, which means less waves are going to be traveling at the right angle to be reflected and instead refract through the cladding and then refract out back into the air or underwater wherever this fiber optic cable is. So the refractive index of the cladding still has to be greater, but it's going to be as close as possible because that will what's the term again? That will eliminate, yes, that will eliminate extreme paths. So this means that that paths that are much longer than the shortest possible path do not exist, and they are relatively in the same range, the length of the paths, which decreases modal dispersion. So like if we do our like analog pulses, as we've done here, for how modal dispersion would affect things. Say we had two pulses, like this, right? This is as it enters, but this pulse, no, sorry, this pulse takes a longer path. The first pulse takes a longer path. Sorry, you can't see that. This would mean that the pulses would actually start to overlap and they would interfere with each other. Do you see how that's sort of come together? And this would lead to an entirely new signal, which would not lead to the same effect that we had here. This is the issue that modal dispersion causes, right? Another way that modal dispersion is removed as much as possible is by the use of the single mode fiber, as we discussed earlier. If the width of the fiber is as small as possible, then the added length from the jagged path or the zigzag path is going to be as minimal as possible. But one last thing that we need to go over is another type of dispersion called material dispersion. And material dispersion is again to do with how pulses are going to travel at different speeds and arrive at different times, except it's dependent on the wavelength or the frequency of the electromagnetic wave used. So say white light enters the core, so I'll just this is our fiber optic cable again. Say that this is white light and it travels perfectly straight. It doesn't even need to bounce, right? So sorry if there was a cut there. As I was saying, red wavelengths travel faster through the cable than violet wavelengths. Although the difference in speed is minimal due to the refractive index, it's still there. It's still going to affect things, and we're going to get something similar to what's happened here, except this time we call it pulse broadening. So if we represent our original pulse, our white light pulse, as a wave sort of like this. This is the bottom of the wave, and we say that this part is the red wavelength, and then it's getting overall brighter and like sort of more violet as we go along, right? What's going to happen due to material dispersion, due to the difference in speed, is pulse broadening. So our wave that once looked like this is now going to be a lot shallower and it's going to be a lot wider. So if we represent this in terms of our analog pulses again, our pulse is going to go from something like this to something like this, wider and shallower. And that's how material dispersion works. And as you can guess, for all these examples, I've discussed the use of white light, but the way that you diminish material dispersion is by using monochromatic light or electromagnetic waves of a singular wavelength, because they won't travel at different speeds, they will travel at the exact same speed through the same medium. And that is the lesson on fiber optic cables. It's a little bit long, there's a lot of stuff that you need to know for it, but hopefully this lesson has helped understand what the issues are with fiber optic cables, what fiber optic cables actually are, and how can we diminish the issues caused through the use of other technologies. Thank you very much for watching, and I will see you all in the next video.